Okay, hi everybody. This is the office hour. And so for the few people that are actually here, yeah. Okay, so first we're going to start with the easy, like very easy questions. If anybody has any ideas, well, we don't have to deal with this one, right? It's like sort of like very easy. So okay, we're gonna start with this in a normal way. Okay, so if I don't mess up, yeah. So for the first one, we're computing seven, if I can write, a 7 to the 100th power mod 13, and we can use Fermat's theorem to get 7 to the 12th to the to the 12th power. Is congruent. It's not working. Is congruent to 1 mod 13. So what we can do is we can convert this to 7 to the 4th power. What the heck? Okay, we can convert this to 7 to the 4th power mod 13, and that's equivalent to 49 to the second power mod 13, which is 10 to the second power mod 13, which is 100 mod 13, which is if I look at this, it's 9 mod 13. Okay, so that's the first question. Is there any questions? Uh, Please do say something in chat so I don't feel like empty or like there's no people here though. But almost. Okay, so that then I'll take that as a no, and we'll move on to the second question. Uh, so the second question asks us to compute 23 to the 1999th power mod 7, and so we can convert this to 2 to the um 4th power, which is congruent to 16, which is congruent to 2 mod 7. I hope that was clear. I took a little less steps because I think it's like slightly more clear this time. Is there any questions for that one? Okay. And for the last one, you can't use Euler's theorem since 6 and 20 have a GCD of 2. So you get to use Chinese remainder theorem, and you split 20 into 4 and 5. And so mod 4, it's congruent to 0. Mod 5, it's congruent to 1. So our answer is 16 mod 20. Okay, is there any questions on that one? Okay, great. I'll take that also as a no. And then Yichen can do the next few questions.
Okay, so those were the easy questions. Now we're going to move on to the medium level questions. Now, so for this first question, does anyone have any ideas? Let me see if the
The
oh,
brilliant.org question.
okay, yeah. So FLT is a great idea. So first, the first step here is like for the first question, P is not 29, okay? Because like there's no way that 29 is divisible by 29 to 29th power plus 1. That's not true. So here we can like change this into the form where 29 to the pth power equals -1 mod P. So here we use FLT here, so 29 to the pth power is congruent to 29. And this is -1 mod P. Now this basically means that P is is this basically says that P is a factor of 30. So this just tells us that P is 2, 3, or 5. If we just check these primes, they all work. So we have 3 prime numbers P. Now for this AIME question, does anyone have ideas for this AIME question? Let me check answers in chat.
The two other people.
Okay, someone got it right though. So does anyone have any ideas for this?
Wait, did they send you the answer?
Yeah, it was like public chat. Okay. I guess not. So here 549 is 42 here, right? So like here we can use Euler's theorem here. So Euler's theorem gives us 6 to the 83rd power plus 8 to the 83rd power. This is congruent to 6 to negative 1 and 8 to negative 1 power. So if I try to use inverses here, then you get 6 times 8 is 48, right? So that means that the inverse of 6 would just be simply negative 8. So this is just negative 8 minus 6 because, well, if 6 times 8 is 48, which is negative 1, then negative 6 times 8 is just 1. So like, yeah, get this. This is just negative 14, which is also congruent to 35, which is our final answer. Well,
Maybe
actually,
hit
0,
the
3,
eyes on B button next time.
oh, sorry. Wait, I just record the whole.
Is there any questions? Okay, great. That's probably a no, unless somebody sent you 10 questions.
Okay, I guess no questions, so. Okay, because apparently the recording had an error, because like we recorded what Edward's screen was on.
It's okay. Just like keep going. We didn't miss much.
Oh, okay, sure. Just look at these again.
It was like right off the edge, but it's okay.
So I guess for the hard questions now. So does anyone have any ideas for this one? Let me just see. Yeah, the message in chat. Um, okay, if there's no ideas here, then I guess I'll go over them. So for this first question, it's an AIME question, and this involves orders. So I think to start off, we can like let order of so we can like let the order of 2 mod p this thing equal d here, right? So after we get this, we can like find out that here because the GCD mn is not 1. So this means that there must be a prime p such that p is a factor of 2 to the n plus 1. P is also a factor of 2 to the n minus 1. We can like convert these expressions into like the mod p form. So basically we get 2 to the m congruent to negative 1 mod p, and also 2 to the n congruent to 1 mod p. So this first thing, we can simplify it into, I guess like square it into 2 to the 2m equals 1 mod p. So from here, now we can define v2 I to be number of exponents of 2 in I. So like for example, like a v2 of let's just say v2 of perhaps like maybe 48. It's a horrible 2. Would be just like this is v2 of 2 to the 4th power times 3. So like it's gonna be 4. It's like that's like how this v2 thing works. And it's actually real, just saying. You can search it up in your free time. It's like related to LTE or lifting the exponent. So here, because like d is the order, right? Then we can like know that v2 of n is greater than or equal to v2 of d, since n is basically a multiple of d. And then similarly, v2 m plus 1 equals v2d, because m, well, 2 to the m is negative 1, but 2 to the 2m is 1. So that means that d is a factor of 2 to the m, but d is not a factor of m. So then we get these expressions. Now we can use casework on v2m. So we can use casework here, right? So if v2m equals 0, then m has 15 choices and v2n is greater than or equal to, wait, what is this? Wait, I'm in typo here. This is supposed to be d. Right, so v2n is greater than or equal to 1. There's also 15 here. Similarly, for v2 m equals 1, 2, and 3 respectively, then m has 8, 4, and 2 choices, while n has 7, 3, and 1. So, and then for a v2m equals 4 or plus, then v2n is greater than or equal to 5. That's at least 32, which does not work from our set of 1 to 30. So basically, we have 15 times 15 plus 8 times 7 plus 4 times 3 plus 2 times 1. Totally, we have 295. So the final answer. Does everyone understand this? Okay, I guess everyone does. That's a yes. So now we'll go on to the last hard question. This one is just a law of case, I'll say. Also CRT, because to calculate F 17, 18, 19, and 20. So we'll do it here. So 100 is equal to 4 times 25. So we just consider this expression mod 4 and mod 25, and then use CRT to get our final answer. So I think first we'll consider mod 4. So mod 4 isn't too bad because we know that F17 is equal to 17, 17, 17, 17. Yeah. What was that? Sorry. This is congruent to 1, because 17 is congruent to 1. Now F18, 18 is even, so this is just 0 literally. And F19 is equal to 19, 19, 19, 19. 19 is negative 1 and the exponent is odd, so it's negative 1. And for 20, 20 is a multiple of 4, so this is just 0. So the expression is overall 0 mod 4. And now we consider mod 25. So mod 25 is a lot more complicated. So start off because F20 is again 0 since 20 is a multiple, no, yeah, it's a multiple of 5. So that's just 0. And then for F18, 18 squared is 324, which is negative 1. So 18 to the 4th power is 1 mod 25. And again, 18 has an even exponent, so this is just 1. Now for 17. So for 17, it's not as simple as the two above. Because for 17, this is 17, 17, 17, 17. Now I'll just write here that phi of 25 is 20. So here we just have to calculate this above thing, which is 17, 17, 17 mod 20. Now, phi of 20 is 8. So this above thing here, 17 is 1 mod 8. So this is just congruent to 17 mod 20. So this means that F17 is congruent to 17 to the 17 mod 25. And then this is just congruent to 22 mod 25 after like some calculations. Now, similarly for 19, we use a similar process also involving these phi's. So F19 is equal to 19, 19, 19 to the 19th power. And well, for this above estimate here, 19, 19, 19, this is simply -1 mod 20, since 19 is -1 mod 20. It's an odd exponent. So then here, furthermore, we can just get that this F19, F19, this is simply equal to, congruent to 19 to -1, which is congruent to 4 mod 25. So if we combine these up, we have uh, this 2 right here, this 4 right here, this 1 right here, and this 0 right here. So this whole question totally is 7 mod 25. And this combined with 0 mod 4, we basically get this as 32 mod 100. Our final answer, 30 or 32. Oh, someone asked me, how did I get 1717 congruent to 2 mod 25? So here it's just like, I guess it's like bash here. So 17 to the 17th power. This is congruent to, well, 289 to the 8th power times 17, which is congruent to 14. Yeah, 14 to the 8th power times 17. This is also congruent to 96, which is like -4. -4. So I pen not writing. Never mind. So -4 to the 4th power mod times 17. And then this is just 256 times 17, which is 6 times 17, which is 2. Does this make more sense perhaps? Wait. Okay, I guess that makes more sense. So now we're done with the hard questions, so I'll leave it to Edward for the challenge question.
Yeah, so time for a very challenging challenge question. Okay, make sure everybody's following me. So this is the challenge question. So ask you to compute the number of positive integers n between 2017 and 2017 squared, such that n to the nth power is congruent to 1 mod 2017. If you have any ideas, please DM me in the chat. Or if you have an answer. I've not received the correct answer so far, so I'll give you 1 minute to do that. Okay, so there doesn't seem to be any ideas yet. Um, well, that's about time. And so I'll go for like how I did it. I have gone like a very close answer. Yes, it's very hard. Um, somebody said a CRT. And that's basically what we're gonna do. But first, we're going to think about it the normal way. And so, um, in this question, I'm gonna make a few quick definitions that maybe won't make the perfect sense right now, but will make sense later. So I'm gonna find A mod B to be equal to the remainder of A divided by B. And then after this, we're gonna define that GCD of 0 and any number is equal to the number itself, and the fact that 0 is divisible uh, by any number. This is probably like um so this is probably like this probably doesn't break any rules you've known. Most of it is pretty like straightforward. The first one is just the definition of an operator. The second one is like if you think about like uh the Euclidean algorithm and go back a step, it also makes sense. The third one, if you go into the definition of divisibility, like the algebra one, it also does make sense. So I hope these definitions make sense. They're gonna help us a little bit. And for this purpose, I'm gonna note that GCD of 0 and n is equal to GCD of n and n. And so we'll be using this fact later. And so we're gonna apply our FLT first. First of all, 2017 is prime. So n to the nth power is gonna be congruent to n mod 2017 to the power of n mod 2016. Does this step make sense? Okay, I'll take that as a yes, and we'll move on. So now I'm gonna define A to be n mod 2017 and B equals n mod 2016. So now our number n to the nth power is congruent to A to the bth power. And so next we're going to show that this is a bijection. And what a bijection is that it's a one-to-one correspondence. So every single number, uh, n can correspond to a pair of A and B, and every single pair of A and B will correspond to a number n. So we've shown the first part, and for the second part, somebody actually put the correct answer in the chat before. We're gonna use the Chinese remainder theorem, and using the Chinese remainder theorem, we can show that for all A and B, there exists an n mod 2016 times 2017, such that n is congruent to A mod 2017, and n is congruent to B mod 2016. And so I might have anyways. So and so to map this back, we're going to have to like, since there's more than 2017 times 2016 numbers, we're going to quickly remove all multiples of 2017 from right here. And so that's like we are removing like the edge cases, and so this makes it more rigorous. But anyways, now there we have a bijection between n and one-to-one correspondence between n and pairs of A and B, such that A is not 0, right? So 0 less than A less than 2017, and 0 less than or equal to B less than 2016, where n is between 2017 and 2017 squared. And so if you calculate it, it fits in the range and all of that. So this is like a projection. And so now we're just simply looking for the pairs of A and B such that A to the bth power is congruent to 1 mod 2017. Uh, and so is there any ideas here about what to do? I know this is not necessarily a step we learned, but in case anybody knows. Do you know what to do here? Also, thanks for the new people that joined. It's not a lot of people, but if you joined, a good job. I have no ideas in the chat. Everybody knows what's happening, right? Everybody understands this first part, right? Okay. But there's no ideas. And so I'm going to use a concept, may or may not be explained in the lesson because I forgot what we did. Okay, so we're gonna take a step that's using primitive roots, and so we're gonna find a random primitive root g. And a primitive root has a certain property that if you list out 1g squared and all the way to g 2016, then it'll generate all the residues from 1 to 2 and all the way to 2016. And this is a property of primitive roots. And now what we're going to do is we're going to, there exists a k such that k is between 0 and 2016. Such that a equals g to the kth power. Oh wait, I think it's like this, right? Okay. Well, let me check. Oh yeah, so it's less than 2016, I think. So actually, sorry here. It's all the way up to 2015. Here, so yeah, this is we can let this here, and so we now have a one-to-one correspondence. One-to-one correspondence between A and B and B and K. So now if we substitute that and get G to the kth power to the bth power is congruent to 1 mod 2017. And so what we're going to do is G to the k bth power is congruent to 1 mod 2017. Does everybody understand this step? Yeah, I'll take that as a yes. Does anyone have any ideas about what we're going to do next? And if you don't know, the next step is completely within the scope of our class. So we talked about it during our lesson. Euler's theorem, not quite, because 2017 is prime. And so the correct answer is for Matt's-Lyell theorem or FLT. And I'm gonna apply that again. And we can use this to show that since G is a primitive root, 2016 divides K times B. And now we're going to take a number theory path of like analyzing the divisors and factors. And so what we can analyze from this is that of the factors of 2016, of those that are not in B, they are in K. So I think this is obviously obvious enough because otherwise a 2016 can divide K times B. And so we can like write this as if we like assume B is like a constant, then K has to be divisible. K has to be divisible by K has to be divisible by 2016 over the GCD of B in 2016. Does everybody understand this step? Okay, so I'm taking that as a yes, and now we're going to list or like count the number of values of K that can satisfy this, given that K has to be greater than or equal to 0 and less than 2016. Does anybody want to like tell us all in the chat what number they got for the number of like numbers of k that are possible for like a b that doesn't change. Also for this you can assume you can use the GCD. Okay, there's no answers in the chat, so I'll take that as nobody really understands this really well or like something. I don't know. So first we're going to take this part, so that's x. So you don't have to write it over and over again. And so 0 obviously works, right? X obviously works, 2x, all the way to GCD B 2016 minus 1 times x. And now if we go over this, we're going to hit 2016 and that's bad. So this is our maximum amount. And so the number we have here is actually just GCD 2016b. Does everybody understand this step? So we're just like listing them out and counting them and finding out that there is a GCD 2016b different values of k that can satisfy this condition for a certain b. Okay, I'm gonna assume everybody understands that step too. And so we're gonna move on. Now we assume the b is constant, so now we're gonna sum over all the b's. And so we're going to sum over from b equals 0 to 2016 of GCD 2016b. So this is our answer. Well, not quite. It's not to find out the answer or the number, but at least like this is like fixed like not necessarily easy to calculate, but it could be calculated like brute force if you like really want to. Okay, I hope everybody understands this. And so this is where our first definition is of this takes in place. And so like you can see here that if right here b is 0, then our k could be anything because g to the 0 times something is always congruent to 1. And so it also makes sense because this will be 0. I mean, uh also makes sense because we defined the 0 um is can a 0 is divisible by anything, so this will also hold. One question in the chat says, can we use that lemma in the handout? But what lemma are you talking about? Is it the like the GCD one with like the yeah. Can we use that? Yes. You can like say it as like a well-known lemma or like a well-known theorem. Not really that many people agree about what it's supposed to be called, but it's like a well-known lemma, or like a lot of people do not. Although I don't see any place where you can use it. If you would uh tell me, I would like tell you if it's like applicable in that case or not. I don't know where that could be used though. Although I didn't like find out all the solutions, so maybe there's another solution that uses that lemma. Although you can use that. Uh, it should like it works. Like it's a thing. Okay, so assuming there's no other questions, I'm gonna carry on here. And we see 2016 twice, so we're just gonna take that out and put like as an x and take it out as a function. G of x defined as a GCD sum of from x and I equals 0 of GCD I x. And so now we're going to change this notation slightly. This is where our thing first came in. So this is supposed to be x minus 1, sorry. And this is supposed to be 2015 here. Sorry for that. we're gonna change this so it goes to x, not x minus 1. And so we're gonna change it to this form. And so we can do a little bit more algebra on this. Okay, is this okay? We just did some algebra here and we like change it to this form. Does everybody understand this step? Okay, so next I'm gonna claim the function g is multiplicative. I'll come back after we find the answer to prove that it's multiplicative and everything, using some advanced number theory concepts. But anyways, I'll just like assume it's multiplicative in the sense that GA times GP equals GAB if the GCD of A and B is 1 or A and B is coprime. So then we can expand this sort of out into G of 32 times G of 9 times G of 7, which can be calculated to be 122 times 21 times 13, which equals 30,576. So that is our answer. Does everybody understand this step? Here, we just like take that. Okay, I'll take that as a yes then. Now since we made an assumption, there's two possible paths you can take. Um, if it's a free response competition, if it's like a calculation, you can assume this is true. Like you don't have to worry. For free response competition, you can either take two paths. The first path um is to like cite it as like a well-known theorem because it is well-known that the GCD sum function is multiplicative. In fact, this function and all about it, including like Mobius series and like Dirichlet things, it's pretty well known. You can search up. Uh, you can search up like GCD sum function, and like basically the first result is like a paper that like explains a lot about it. It's a quite advanced number theory function. You can search up a lot of things up about it. Normally it's like talked about with like Mobius function, uh, which is like a weird number theory-ish function, and Dirichlet series or something like that. And it's quite a famous tool or like function in some sorts. But anyways, we're going to head into the detailed proof about it. Although I'm pretty sure no one cares at this point, but I'll still talk about it. Okay, so now we're going to take this sum formula right here, x of GCD I and x. So we're going to enumerate over the possible values of this. So for any possible I, if we let E equals the GCD of I and x, then there has to be a couple important conditions such that I over E is an integer, x over E is an integer, and the GCD of these two equals 1. So I'm pretty sure this is correct. Is everybody following me at this point? It's okay who knows the answer. Okay, I'm glad somebody is at least following me. Okay. Okay, so next we're going to um enumerate over this. So we're going to count how many i's satisfy this. So what we have here is that these two are co-prime. And so if you look into it, sort of, x is bigger than I, so we can take the number of I over E, which equals the number of I, since dividing is a well-defined function. The number of I divided by E that satisfy this is equal to the totient of x over E. Does everybody understand this step? It's literally the function. Like literally the definition of totents. And I hope whoever was following me is still following me. Here's everybody. Follow me. Okay, great. So I hope this all makes sense. And so we're going to quickly put that back into the summation. And notice that this e does have to divide x. So we're going to change it into like this weird summation notation, which means we're summing instead of summing from a minimum to a maximum or summing through a list or something like that, or summing through all the factors of wait, it should be the other way. Sorry. We're summing over all the factors of x. Like for all e that divides x, add them to the sum. It basically means that. And we're summing of x over e, and we're multiplying that by e. So this is our sum we just like enumerated over our GCD. So like for every single possible GCD or e, we are going to make a separate term for that. So just here. So like if like e is like 2 and like x is 4, then we're adding up all the terms such as the GCD is 4. I mean the GCD is 2. So I hope that makes sense. Does it make sense? So if you are saying yes, I'm gonna carry on and do some substitution. So in this case, there's a one-to-one correspondence between x over e and e. So we're going to define d to equal x over e and move it into like this form. The sum of d divides x, phi of d times d times x over d. Does this make sense? Okay, I hope the next step makes sense, although it probably won't. So this is if you haven't taken like a very advanced algebra number theory course, you probably won't know what this is. But if you recognize that this is the Dirichlet convolution of integer functions, and search it up on Wikipedia or something, because that's great. It's the Dirichlet convolution, which is denoted by like the star thing of the totient function and like the identity function or y equals x. And this is equal to this of x. So I hope this makes sense. And if you don't know, the Dirichlet convolution of two functions f and g is equal to the sum over the factors of x of f of x times g of n over of x over n. Sorry, it's supposed to be an n. Does anybody see how these two functions like basically fit in the same form? Okay, I think that everybody understands this step. And so after we take this, we proved in the class that the totient function is multiplicative and the ID function is obviously multiplicative. And so if anybody is searching for the spelling of Dirichlet convolution to search it up, I'm gonna quickly type it on the screen here. It's like Dirichlet convolution. Oh, it's telling me to sort of spell it wrong. Let me fix that. If it actually is spelled, I don't think it's wrong. It's like Dirichlet convolution. Dirichlet is a famous mathematician that did number theory and calculus. It's like obviously convolution is like a calculus concept, but Dirichlet convolution is used more in number theory because it's quite different from normal convolutions. Okay, anyways. So after this, after you see this, there's this very famous property that if you take the convolution or Dirichlet convolution of two multiplicative functions, then the resulting function is multiplicative too. And so that proves so G is multiplicative. Does everybody understand this step? Okay, so that's great. And if there's no more questions, then maybe we'll end it early unless somebody wants to like talk about something.
Okay, I'll just mention that like for like non-proof competitions like here like you just like don't prove this because like it's not worth your time though to like prove these things because it's like doing like
Well,
non-proof
like
things like
you should
was
know this. Like if you really like need this, you should know it's like a famous. Let me search it up for you.
yeah like for like non-proof things like just don't prove it if you don't have time to because like it's not worth your time.
If you look in like I'll send it to everyone. If you look in like this link here, from the University of Waterloo, it talks about it's like a whole paper on like the GCD sound function. And if you scroll down to like basically like the third page on the very bottom, it talks about this right now. It's like basically how I proved it too. Yeah. And if you search up the Wikipedia page on Twitch like convolution, you'll find something. If you search it up, uh, it says here, um, wait, the Dirichlet convolution of two multiplicative functions is again multiplicative. It's like if you go look at this page, AOPS wiki. I don't know. So AOPS servers are really laggy
Perhaps there
nowadays.
also is one. It's pretty short though. Just wait, that wrong thing. Wait for it to
Uh,
also like
AOPS is being very laggy.
yeah, it's right here. It's quite short though, like not much stuff to read.
Yeah, that's why you should go to that paper I sent. It's like quite long. So it talks about like the Mobius functions. Um, why is there no page on GCD sum function? If anybody wants to, I can also talk about a normal convolution. Does anybody want me to talk about normal convolution? I'll burn like the last 8 minutes of time talking about normal convolution. Oh, what? This is so short. Okay, anyways, we're going to talk about normal convolution. And so normal convolution is when you do this. Yeah, I know. We're talking about discrete normal convolution first. Oh, what? What is this? Um, okay, I don't want to know that. So before we jump into integrals and calculus, we're gonna define the normal convolution of two real functions f and g as of two change the page. Okay, sure. Okay, we're gonna first define the normal discrete convolution of two integer functions, f and g. X equals to the sum of all from I equals 1 to x minus 1 of fx times g of uh x minus I. Sorry, this should be an I. Let me search it. I'm not sure. Not sure what it's supposed to sum from. So yeah, it's from sorry, it's from negative infinity to infinity. How could I not know? That was sort of obvious, but whatever. Negative infinity to infinity of like this. So basically what you do, for example, are taking the convolution of a function that's like this. Remember, these are integer functions, so they look like star steps, right? And with a function that looks like, if I change the color, something like this, Well, what you do is you reverse the second function into something like this. Um, and then you, for each of these, you multiply these two values, and you multiply these two values, and you multiply these two values, and you multiply these two values. And we're assuming this extends off to infinity, right? So if we're calculating like the on 4, then we're flipping with respect to 4 over 2, which is 2. So we're flipping over this line, which I did in this case. But anyways, so I flipped over that line and we multiplied them together and added to get something. I'm not gonna go like too deep into this or whatever. And so instead for continuous functions, this like summation notation no longer suffices. So we're going to change it into some fancy integral notation. Equals the integral from negative infinity to infinity of f of f of, oh wait, sure, I can't use x in this case. We're going to use the Greek letter tau because that's what everybody uses. Um, d tau. And so this is our definition of the normal convolution on continuous normal functions. And so this is used in edge detecting, image processing. Also, yeah, you can search this up, but this is like normal convolution. It's like quite like a sort of fancy thing. Um, yeah. Should I talk about like the statistics of convolutions? Okay, now I'm gonna talk about combinatorics and number theory because we have like 3 minutes left. Nice. So if you're talking about like if you're talking about rolling die like discrete outputs, if you want to like say what is the probability of like rolling 100 on like 50 dice, then we're going to take the convolution of rolling die. So like the probability of rolling 100 is basically the convolution of like rolling a die, or like the probability function. If you like don't know what that is, it means like um if for like discrete values, e.g. this one, if you roll a 1 and the probability is 1/6, then that is just 1/6. And for like 1 and 2 is also 1/6, 3 is also 1/6, but they might be like uneven like this, sort of. So anyways, that's like the probability function. And so we're gonna take the dies and take the convolution again and again until we have like 50 of them. And so what's gonna happen here, if you take the convolution and for the resulting function, if you take it at 100, it's just specifically the case for like for 100, like what's the probability? Or it's also like I don't know. Anyways, that's like the combinatorics view. For like if it's continuous, if you take a convolution with the probability function defined using integrals, then it's you get like if you like add them together, then what's the probability and like something like that, I think. It's just like a nice little it's regarded as an elementary arithmetic function, although you're never taught it in elementary school. Um, but it's like quite fundamental. It's also very complicated to evaluate. Okay, there's like 10 seconds left, so I'll just like wait.